Our next paper, the title of next paper is assessing the effects of DER on voltage using a smart meter driven three-phase low voltage feeder model. The presenter will be Wang Yiqing Wang. I think Yiqing is here, right? Okay. Yeah, Yiqing. Okay. Welcome you to here. And I give Can you share your screen? Share your slides? Okay.
Yeah, sure.
Not your face, your slides. Okay.
Okay. Yeah.
Yeah, perfect. I can see your slides. Yeah. Wang Yiqing is a master student in smart grid at the University of Melbourne, Australia. While she is working on using smart meter measurement to assessing the impact of the DER on the customer voltage in the low voltage network. So Yiqing, please give your presentation. Please keep your time within 15 minutes. Then we can have 5 minutes Q&A session. Okay, so you can start now.
Okay.
Thank you.
Okay. Yeah. Hello, everyone. I'm Yolanda from University of Melbourne, and this work has collaborated with Dr. Michael Liu and Professor Luis Nando Ochoa. So this presentation will show the work in assessing the effects of DER on voltages using a smart meter-driven three-phase LV feeder model. And this presentation will give you the outline, which is the background, and then talk about the research question, the proposed methodology, and the case study. And finally, I will give the conclusions of this presentation. So let's imagine a conventional LV feeder. So it carries electricity from the distribution transformer to the residential household. And then as the red arrow shown here, we can see a voltage drop along the feeder. And it should be noted that different countries have different voltage levels. And in some places of Australia, the voltage level is 400 line-to-line voltage. But things has been changing in the low voltage network, and due to the technology development, we start to see the smart meters and also DER in the low voltage network. And the DER in this work refers to the solar PV systems. So when sun comes out, they start to generate electricity for household uses, and the surplus solar energy will be injected to the grid. So as the blue arrow show here, that means the voltage will be rise in the low voltage network, which is different from the previous conventional LV feeder. So the challenge is that when we increasing the penetration of PV system in the low voltage network, we start to see the voltage rise like also increasing. So which will eventually over the upper voltage limit. And that is not what we want, because the household appliances and also distribution transformers will be burned out. So the distribution company who actually own the low voltage network, and they don't want any they have to ensure the network integrity. So they have to check the voltage and to understand the impact of DER on voltages. So they are increasingly want to do what if analysis of DER, and before they can take any action to avoid voltage variations. But actually, there are some challenges in the low voltage network. So first, in the low voltage network, we usually don't have a model. So even though we may know the customer location and how they connect with each other and how they connect with the distribution transformer, but sometimes the impedances in the low voltage network is poorly recorded. So that's the reason there are so many researchers have been invested in this area by using smart meters to estimate the impedances. But the problem is that they don't consider the phase couplings like in many studies. So that means that existing literature can only be used in the balanced three-phase network, the single phase, and that is not a realistic and balanced low voltage network. So the research question is that, can we exploit smart meter measurements, and in order to help us to estimate the impedances of the three-phase unbalanced feeder? And once we have that, can we calculate the customer voltages in terms of their certain injection or absorption? So for example, this household want to inject 5 kilowatts to a grid. So can we help it to calculate the voltages, and in order to help distribution companies to assess the voltage and avoid the voltage violation issues? So there are two parts of the proposed methodology, and the first part is periodical impedance estimation. So given that impedance, they don't always change with time, so we can actually estimate the impedance every 6 months or every year. And the basic assumption is we assume having the knowledge of the head of meter measurements, which is the active power, reactive power, and the voltage magnitude. And we also like similar as here for the smart meter measurements. And another assumption is we assume having the customer location, which is their distance to the transformer and their phase connection. And the final assumption is we know the service cable impedances. So in order to estimate the three-phase feeder impedances, and here we use the three-phase linearized voltage drop equation with multiple linear regression. And this is the impedance. And after that, the second part is once we have the impedances, we can calculate customer voltages operationally. So this customer want to inject certain power to the grid, and then they can use the estimated impedances, and they can use the power flow engine to run three-phase power flow and to give the voltages for the companies. And distribution company, they can check the voltage, whether it's within the limits or not. If not, they have to take actions. So before I explain the proposed methodology, so here I want to give some background and information about the LV feeder modeling. So on your right side, which is a general LV network, and the black line shows the three-phase 4-wire LV feeder. And residential households are usually single phase, and they connected with the three-phase 4-wire feeder using the single-phase 2-wire service cable. However, here in order to reduce the computational time, when we have to reduce the impedance variable, but we have to make sure it works in the unbalanced network. So here we use the Cron's reduction, which assumes the neutral wire is connected to the ground directly. And the impedance matrix for the three-phase 4-wire line is represented by a matrix, which is 3x3 matrix. And the diagonal line shows the self-impedance, and the off-diagonal line shows the mutual impedances. And here it should be noted that we assume they share the same self and mutual in order to reduce the impedance variable and in order to reduce the computational time. So similarly, for the single-phase service cable, we also using the same way and to represent it by a complex number here. So after this, so the basic concept of the three-phase LV feeder impedance estimation is simply explained here by a single phase line. So assuming that we know the terminal measurements, which are active power, reactive power, and the voltage magnitude. So the relationship between the impedance and the meter measurements can be derived by using the classical linearized voltage drop equation. But the question is that how we can estimate two impedance variables by only using one equation. Well, the answer is from the smart meter measurements, because smart meter, they can provide multiple time series data for the active power, reactive power, and voltage magnitude. And that means we can make a multiple linearized voltage drop equations. And then we can put this input data to the multiple linear regression, and they will help us to find the best fit for the coefficient, which is the resistance and the reactance. But the problem is that can we use it straightforwardly to the three-phase network? So actually it is not, because we don't have the terminal voltage, which is the three-phase bus voltages, and we also don't know the power on each segment. And the most important thing is single phase, they don't consider the three-phase couplings. So the proposed methodology, how to calculate those input data. So the first thing is the three-phase bus voltages. And given that we have the smart meter measurements here, and we know the sorry. And we know the series cable impedances. So we can use the linearized voltage drop equation to calculate the voltages at the red node. And then given that we know the distance, so based on the assumption that voltages can linearize change with the voltage linearize change with distance, we can calculate the voltages at the yellow node. So after the voltages we already know, we can calculate the segment power injection based on a series of equations here. So I'm not gonna go through all of them, but the basic idea is based on the power balance equations. And the important variable here is the losses of each segment, and it's determined by the total feeder losses, and their relationship is similar to the voltage drop square of each line to the total feeder voltage drop square. So after we get the voltages and we get the power, then we can use the three-phase linearized voltage drop equation. So like the similar way as the regression, then it helps us to find the best fit of the coefficient. And then we get the impedance, which is the self-resistance, self-reactance, mutual resistance, and mutual reactance. So this proposed methodology has been used in a real Australian LV feeder. And here you can see there are 40 customers in the low voltage network, and they connected with the three-phase feeder by using 10-meter series cable. And the data is from one of the distribution company in Australia, and here is the demand, and the bottom figure is the generation of the PV system. So the impedances has been estimated and 50% PV penetration, and the accuracy is assessed by calculating their absolute percent error. So here, as you can see, the box plot, which is the error for the self-resistance, self-reactance, mutual resistance, and mutual reactance, and their median error is less than 13%. Once we have the impedances, we calculate customer voltages and 100% PV penetration. So this is our what if scenario. And the calculated customer voltages compared with the actual customer voltages. And as we can see, the voltage mismatch is quite small, and the maximum median mismatch is also less than 0.005 volts. So which means the proposed methodology is quite promising. So the conclusion of this study is that even though there are some challenges when you do the voltage calculation because we don't have the phase couplings in the impedance matrix, but it can be solved by the proposed methodology. And also the voltage calculation depends on the accuracy of the impedance, and based on the results is quite accurate. So it can be an effective tool to help distribution companies to calculate voltages in what if analysis and to assess the impact of DR in the low voltage network. So the further improvements is that maybe some places they don't have the series cable impedance. So can we help them to also estimate the series cable impedances? And also, given that power flow engine maybe calculate the voltage quite slow in a general LV network, so can we help them, like for operational purpose, can we help them to develop a quick and accurate voltage calculation approach by using the estimated impedance of the LV lines? So that's the presentation. And I will acknowledge the co-author Michael and Professor Luis Nando Ochoa. And thank you for your time. And do you have any questions?
Okay, Yiqing, thank you so much. We have one question. Can you see this question?
Just give me a sec.
Yeah.
So
it's about different style of the feeder, because he mentioned that maybe your method is generally used in North America. Can you consider the different type of the feeders in Australia?
Can I read it? Current reduction is generally used for North American style feeder. Have you considered an impact when you are using same for which is? So now I'm using the Cron reduction in my proposed methodology. So I think it is quite suitable for the unbalanced network analysis. It's adequate model. So I'm not, so.
Okay, maybe we can discuss this question offline. We have the second question. The second question is related to accuracy. Can you see that? How do you see that?
How do you think the accuracy of the impedance estimation regarding to other aspects? So impedance estimation can be used in many places, like in state estimation also, not only for the voltage calculation. So if you have impedances, you can do many things, because in low voltage network, we usually don't have the model, and in particular the impedances. So if you have the impedance, you can do like a planning purpose or operational purpose. So it's not only for the voltage calculation.
Okay. The last question also related to the accuracy. If the errors are around 13%.
Which one?
The last one, the third one.
So if the errors are around 13% for many of the parameters, and results in less than 0.01 per unit voltage estimation errors, does that imply now that parameter estimation in the separate is not important, which is good outcome? I think the errors around 13% for many. So if I think for the self-resistance, the error is really small, like much less than 13%. You cannot say it's not important, because it is quite important to for the voltage calculation. But for the certain impedance variable, for example, the mutual, for example, the reactance part in the low voltage network, you can say it is less important than the resistance part. But for the impedance estimation, it's quite important, like for the distribution companies to calculate voltages. So the resistance accuracy play an important part for the voltage calculation. So is it solved the question?
Okay. Thanks, Yiqing. Sorry for the limitation of time. We have to terminate this interesting discussion. So I think the Yiqing's email. We can find Yiqing's email on these slides. So any further questions we can discuss offline. Okay. Thank you.
Okay. Oh,
Thank
you.
Thank you.